minutes or so are dedicated to showing you how I solved the task that I assigned you last time. And I need to clean up a bit the notebook, but then I will upload it online today. Now, as I told you last time, I won't focus this course very much on radiomics, so I won't spend too much time on that, but I think it's useful to see that, so let's see. Now, okay, so we were left here about the display with the overlap and the transparency. And I was showing, and here I showed you how you can call the feature extractor by Radiomics, which when you call gives you back a large number of metrics. Now, in this version of the notebook, I worked with just with NumPy vectors. You can also save your results in a panda structure, so maybe it's cleaner to read. Okay, so, but filling pandas in a loop is always something which is not super good. So these are my results. The first things that I did, it's just a comment to what I've told you when mentioning the theory. If we do a scatter plot of the features, we can see that many of them are highly correlated. So starting from light green, we have 80% R squared. 80% R squared means that with a linear model, you can explain 80% of the variance, which means they're basically the same thing. Now, what I personally did was, after getting all these features, just taking a random forest classifier, which does not need to scale all features in a normal range, and also, given all the internal cross-validation during the fitting, should not benefit too much from data reduction and data normalization. I just straight put the numbers in it, and I get a 80% score on the validation data set, which is pretty good. Now, what I did next was to try what happens when I drop all the columns that are that have too high correlation. And here I discarded only the columns with an R squared higher than 90%, which means even more identical. And I get half of the feature. I also saved in output all the names of the columns that remain. And in this case, I'm not sure whether it's random or not, but I get a 2% increase in accuracy in the validation dataset, which is nice. And then I also tried another technique, which is to use a feature selector. As usual, even just in scikit-learn, you can find I guess a dozen of feature selectors. Here I used the one that takes in input a classifier, and from the classifier it finds the most relevant features. And I told it to just retain 5 features. And in this case, out of my validation accuracy in this case did not improve, but I'm still at 80%. Probably one could start tuning the hyperparameters, especially the numbers of features retained. This is an unbalanced data set, not massively, but anyway it is. And so it's on top of the accuracy, you might want to check multiple metrics. And especially in this case, I use the confusion matrix, and we can see that basically there is no misclassification of high grade into low grade, but on 10% of low grade cases, here it's misclassifying low grade as high grades. Now, the last thing that I added here is just to show a proof of, something like a proof of principle. I just did, I just had features on the shape computed. So instead of all the textures, the texture patterns, I just told the class, told my Radiomics feature extractor, just give me the descriptors of the shape, which is just these 1, 2, 3, 4, 5, 6, 7, 8, like 15 features related only to the shape. They don't analyze what's inside the image. But what I did was to compute it on 3 different labels, because in the segmentation we have 3 different labels. Before I was getting the whole region, the union of all the labels. And so we have much less features and that do not interpret the image in any way. And okay, and what we have here is the feature also here are correlated. Some of them are correlated. And by working only on the shape, but of the 3 different subregions, I can get a classification accuracy of 90% on the validation data set. In this case, it means that probably most than the radiomics itself, the analysis of patterns, even just looking at how big the lesions were, could have been sufficient. I tried the same things as correlated feature reductions and most important feature selection, and I kept 5 features. These 5, 2 on label 0 and 2 on label 3. And what I have is that I'm still able to get an 82% validation accuracy on this classification task. So this is all that we will see on the radiomics. We will use the BRATS dataset again for when we will discuss about image segmentation. Any question, or more specifically, any problem that you had in running this? Did you get specifically high accuracy? Did you use any classificator with which? Did you get anything that you see is different or that you want to discuss?
I tried to use a class regression.
Okay.
And I reduced the training set to like 7, 8 features.
Okay.
And I think that would be interesting for seeing which variable are most useful.
Okay.
And interpretability.
Did you get which?
I get about 82.
Okay. Apparently we are.
But just for the part of the explainability.
Okay. Now, probably when we can, like if we are able to retain good accuracy with 5 features, like even in this first case, which by the way, it's interesting to notice that it was also here keeping 2 shape variables. There, maybe not using a random forest, but a simpler classifier, probably one can have a very good a very explainable model. Okay, other questions related to that? Okay, if not, we can get on a different topic. We will open a new part of this course. And just let me pick the presentation. Now, for that, I will try what data, well, I mean, what people now call inverted classroom. So I will give you like 10-15 minutes introduction to the topic. I will leave you with a laboratory task, and then we will do the theory after you did your task, and we will comment on what you get. Now, I have these around 10 slices about deep learning because you probably heard a number of things about that, but last year I've been told that not everyone looked at so everything, so we will do this refresher, which for some of you can be very trivial. Now, the basic of deep learning now is neural networks. And the most important property of neural networks, always to keep in mind, is that neural networks are universal approximators. Given that you have at least one hidden layer and some nonlinear functions, a neural network can approximate every single existing function. Now, originally, multi-layer perceptrons worked this way. A single neuron was a sigmoid, an activation, which is a nonlinear function, which computed an output, which in this case was bound between 0 and 1, given a sigmoid, as a function of the weighted sum of all its input. The interesting part was that it's possible to backpropagate a so-called training loss from the output to the input and to estimate experimentally all these weights. And then you can approximate every single existing function. As you can imagine, it's pretty hard when you're working this way to apply this on images. Because an image is, even small images have 1 million pixels. And if you have 1 million pixels, it means that for every neuron, you have 1 million weight. If you need to have multiple weights, multiple neurons, multiple layers, that easily explodes in terms of memory. What comes to our mind is that we can use convolutions. A convolution, mathematically, is a sum within a small, well, not necessarily small, in neural networks it's small, is within an area, and then move. This operation is intrinsically shift variant, and this is of a special interest in image processing, because it's assumed that's again an assumption. It's not really, it's valid up to a point. We assume that everything makes sense in an image in relation to its context, its near and larger context. So we want to see what's happening in a certain area. So an object can happen everywhere in an image, not in a specific location. So it wouldn't be meaningful to hard code look something in this place. It should be look if a cat is present in any part of the image. So a convolution, in this case, is this kind of weighted sum. We have this image here and this so-called kernel here. We take this and we sum all elements weighted by these numbers. Then we move and go on and go on. What we can do with that is, as an example, we can do a convolutional classifier. You take an image, like 128 times 128. You run a convolution, a 3x3 convolution, and you maybe run a number of them in parallel. So in this case, 32. You run yet another one. And now a pixel in every channel of this image has been informed somehow by its 9x9 background, because it contains a bit of information from here, from a 3x3 of these images, which again was informed by a 3x3 in this image. So you're getting information and interaction from a larger area. Then we can do a downsampling and say, okay, we don't need this high spatial resolution. Let's keep just 1 pixel out of 2. Again, you do a convolution. So by the time that you're here, almost every pixel here is informed by all of the pixel in input if your image was just 128 times 128, because here we are informed by the time we are here, we're informed by 9 pixels here, which were 9 by 2, 18 by 9, so you're almost there. You can keep on going this way, and then if you need to do a classifier, we say, okay, in this layer here, all data points have been informed and related to everything that's present in my image. These are very abstract features, while probably here they are, well, not probably, they are very local features. Let's put these numbers in neural networks, in a standard neural network with neurons, and work in a simple way and get any kind of output that we might be interested in, like a classification task, a regression, or so on. What we can actually do is anything in this list. We can run a classifier. We get an image in input, and we want a class as an output, whether it's binary classification or multiple class. We can get from a class to a number, which is a regressor, a simple toy experiment that one could do, or that maybe we will even do, can be taken a Mars slice and get in output the age of the participant, and it works up to a certain with certain precision, which is probably higher than you expect. But you can actually do anything. You can do semantic segmentation, so label all the region. Instant segmentation recognizes something that you want to see whether it's present, or even image denoising, or we will see that later, even other things. Now, how do we do that? The basic of it, which is up until the advent of transformer, were the way you processed all images, but convolutional neural networks still have their place in imaging. They are very robust, and they don't necessarily need a very high number of training. You do what I was telling you before. You get an input, and you keep on going to a very higher level of abstraction. Then you start upsampling. You just do the transpose of everything you've done here, and you get an output. Now, the issue with that is that it takes really a lot of work for the network to encode very high-level features like edges which are present in the input image, put it here in these extremely low resolution vectors here, and then decode them back to the image space. Now, keep in mind, it's hard, it's not impossible. When you need to do some unsupervised learning, which is very useful sometimes in medicine, you do that, and it works pretty well. However, the invention of UNet was to add these so-called skip connections, where you just add features at the same level of abstraction from the input to the output without the network having to encode them at the low level and resample them. And this, the intuition is that this preserves much more easily the high-level features. So when someone asks you to build a plain vanilla UNet, you just need 2 parameters to be asked: the number of filters of the first layer, because every time you go to a higher level of abstraction, every time you downsample or upsample, you multiply the number of filters by 2, or divide by 2 if you're upsampling, and the number of levels. So this is 1 level, 2 levels, 3 levels. The application of the UNet can be multiple. One application, which we will test later on in this course on the Bratz dataset, is semantic segmentation. You have an image in input. You do stuff with your network, which I've depicted as a black box for reason that you can imagine. And you get an image, and you get a map of labels in output. However, the question here is how can we use multi-channel images? We have seen the Bratz dataset. We have, for each subject, we have 4 images. And actually, well, there are multiple options to do that. But you can just stack the 4 different images as they were different channels, because they are just simply different channels, and the network learns how to combine the information from multiple images at the same time. You should also keep in mind that MR studies are 3D or 2.5D if you want. And what you can do is, again, either use 3D convolutions. However, this takes a very large amount of memory. It's something that can be done nowadays, even on gaming, very high-level gaming GPUs, but not less than that. You can work in 3D, but it's pretty slow. Or you can work, if you want to work slice by slice, you can concatenate, as they were multiple channels, just 2 nearby slices, and this will improve accuracy. Now, you need to keep in mind that while, despite the UNet being from 2017 or so, the theoretical introduction, nowadays there are multiple validated medical devices validated for clinical use, which are approved for multiple tasks, like organ delineation. You get a CT scan, and you get a software that automatically defines the boundaries of the liver, the stomach, or whatever is your task, or some lesion recognition. Another application is denoising, which is the task that we will do today. And we can get, we said that we can get an image in input and an image in output. So you can just bluntly get the network and tell the network, learn if you have a low noise ground truth, at least in the simplest form. We can see when you don't have it, what you can do. Say, okay, here's an image in input, here's an image in output. Learn how to transform a noiseless image, a noise image in a noiseless image. And you can see here the differences, also with some level of zoom here. You can see how we have the noiseless image, so high quality image, an image acquired with a much faster scan, which has higher levels of noise, and we can see the results. especially here they uploaded, they highlighted a specific GRUs of the gray matter. If you're interested, you can see these a number of tests on an interesting article about that. Now, another application is domain transfer. Again, this is not, this is even something that's for which I guess there are approved medical devices. Now, suppose you have an MR scan. It's easy to have brain MR scans because they are acquired for a number of reasons. They don't have any radiation. But in some cases, it's useful to have CT scans of subjects, especially if you are working in radiation therapy. You need to have a density map to plan the radiation treatment radiation beam. And so you need an attenuation map. And what you need to do there, either you acquire the real CT, which, however, takes radiation dose and it's another exam, and you say, okay, I start from NMR, which has many more anatomical information than I need, and I ask to a neural network to get in output a CT scan. Here it's showing together the so-called synthetic CT and the real CT. And it's relatively interesting to look at the lower slices of the head, because if you go at the higher slices of the head, every head is the same. The bone is basic, which is the most interesting part for radiation therapy, because bone attenuates radiations. It's just a circle. So for a neural network, it's pretty easy to know where to put the circle. But here in the lower part of the brain, around the temporal bone, the bones have a very intricate structures, and they interact a lot with air. And air and bones in CT have exactly the same signal, which, by the way, is 0. So they are hard to discern. And we can see how the neural network just have to guess what's inside here. There are a bit of differences between the two here. Let's see, all the structure, the nasal, all the structure inside the nose here are missing. And around the auditory channel, we can spot something probably. I'm not that. I mean, these bones here have different structure. This is thinner. And you know, when the information you want to extract is not present in the original image, the neural network cannot do too much. And we'll come back in the next lecture when we will see the theory about that. By the way, in previous courses, did they teach you the conceptual mathematical difference between, let's say, regression artificial intelligence and generative artificial intelligence? Okay, I will put one slide about what's the difference. We will not use generative AI in this course, but we will remind what it is and which limits this gives us. And so now this is a very crucial point when using artificial intelligence, especially in images. As a system which deals with a very high dimensional space, what we say in general is that an artificial intelligence method wants to recognize all the possible correlations and relations between data in some abstract space. And so the question is always, in the original image, do we know, is this pattern somehow recognizable? So if I take a look at the structure of the brain, do I have some information about where the bone is passing? I don't know. We do know that in MR, for some reasons that are not fully, let's say, explainable, it's possible to recognize the age and the gender of the person that you are scanning. And this probably somehow gives some bone structures some differences. So let's say an older woman probably has a slightly thinner bone than a young male, but that's it. It won't tell you exactly the shape. So it's not that clear always whether the information that we want are present or not in an image. Now, let's go back to the task on this. Let's go back on the core topic. When you do image-to-image transformation, you can do some exotic application. You can really take from a random input any output. So what some people invented was to get to estimate the formation field for image registration. Registration means superimposition on a standard atlas. So in this case, for brains, there exists an atlas defined by physicians that tells you a standard brain shape. So you can get a neural network that takes an input, an image, and gives you an output, a deformation field. There's nothing really that prevents you from doing that, and it works quite well. Now, let me give you some, just briefly touch the topic of data augmentation. We know that the neural networks are intrinsically prone to overfitting, especially when you have your data set is limited and your network is very high. Is very high dimensional. You have lots of parameters. The thing you can do is to invent some extra data. Now, you cannot invent data that you do not have. At least, I mean, I've had some discussion with other people, even in startups, that were selling networks that invented training data. I don't think that's really what they want, really feasible. But what you can really do is to modify artificially your input images so that a network does not learn something. You are teaching the network to be robust against irrelevant features. You are adding features that you do not want your network to learn. This process for images is a bit handcrafted. So in most cases, some transformations are trivial and safe to add, like rotations, translation, adding a bit of noise similar to the noise that you might have in the acquisition. For natural images, for camera images, you can definitely change sharpness, intensity, contrast. For medical images, sometimes you can, sometimes you cannot. You should think about it, depending on your acquisition modality. And you can add some artifacts specific of your modality so that your network learns not to focus on that. And yeah, just to comment that this is a bit uncrafted, takes a bit of CPU, but it can really be useful. Now, to wrap up, the thing that you need to remember, and we will come back to that in the next lectures when you analyze what you have achieved, networks are universal approximators. We said that in the first slide. So what they do is to exactly and do exactly and blindly what you ask them. So you need to be quite sure about what you're asking them. As a consequence of that, the choice of the loss function is fundamental. The training procedure is fundamental, like the dataset and the augmentation. And in many cases, we will see that the network, no, we will not see that in this course, but it turns out that the network architecture is not that fundamental. Maybe some structures can be trained faster. Some structure work with less parameters, but nowadays, pretty much any network with enough parameters that you can make up will work. Now, as I said, we will try an approach according to whether you are not used, whether you are very used or not with. My solution for that will be in Keras, whether you are you can work on your own or not with Keras. You can. I can show you how to do some steps. I already have the code here. I have prepared and uploaded online some files, one data through, which contains 2000 MR slices that you can use as reference, keep the first as training and the latter as validation. Then I have two data sets, which are modification of the same slices with normal uncorrelated noise, normal as in normal distribution. And they are at two different levels. And this one contains different levels of noise. Now, you need to implement your network thinking about especially the choice of the loss function, the output layer activation, if you need to do any scaling on the input. And you should experiment after, when you have the first network, on different levels of noise. If you train only on one of the two levels of noise, how does the input react on the other levels of noise? And when you have the two networks, when you have a network that works on the both levels of noise, you need to look carefully at how the noise images that were starting from high levels of noise look like. By the way, I'm recommending you to do this because you can do whatever you want depending on which computational resources you have. Sadly, we are not able to provide you with GPUs this year yet again. But this network can be quite efficient in denoising, quite effective at the task of denoising the kind of input that we have. And like I have a laptop from 2021 and it runs on my CPU in minutes. I can do a training in 5 minutes on my laptop without any GPU. So I don't know if you are using a free collab or things like that, don't waste GPU minutes for that. Even if the CPU on Colab is relatively limited, so it works quite slower on that. Okay, so do you have any question about this task? Do you think you can start alone, or do you need some indication?
I just want to ask you if denoising and also doing transfer in general can be considered like a pixel-wise regression, and if we can use metrics like loss function, like the ones for regression.
Yes, absolutely. You. I mean, it's. Yes, what you want to do. Oh, and by the way, to evaluate the quality of the denoising in what is done in general, even if it's suboptimal given what I told you in the first lecture, in the end is to on the papers what they do, because it's an approach with a number of limits, but it's the only one that we can have, is to take a look at the best mean square error. Or you can look at the similarity index metric, but I don't think that this is a good metric for the loss, because it's not easy to propagate. the loss. It can be used as a metric, but not as a loss, that one.